Rules, formulas, procedures written in code give computers the power to make the best decisions possible quickly and efficiently. They're so effective dealing with data, a new book suggests humans should consider adapting some of those strategies for our own lives. Algorithms to Live By, The Computer Science of Human Decisions, is written by Brian Christian and Tom Griffiths, and they join us now for more. That's Brian on the left, Tom on the right. Gentlemen, good to have you here at TVO tonight.
Thank you so much.
Okay, let's start with this. Are computers smarter than humans?
No, I mean, I think one of the things that is kind of a misconception that we have when we think about how computers solve problems is that we imagine them, working exhaustively through every possible option, calculating all the way to the end, always coming up with a perfect answer. In fact, one of the things that we explain over the course of the book is that up against, real-world problems, the hardest classes of problems, what computers do looks an awful lot like what we do. They take chances, they kind of weigh the costs of computing longer against the cost of making an error, and they use approximations. And so because these strategies resemble what we do when we face a hard problem, there's a real opportunity for us to learn something about how to make better decisions in our own lives.
Tom, let me quote something from the book here, what you write about trying to make choices and how people do that. Every harried renter, driver, and suitor you see around you as you go through a typical week is essentially reinventing the wheel. They don't need a therapist, they need an algorithm. The therapist tells them to find the right, comfortable balance between impulsivity and overthinking. The algorithm tells them the balance is 37%. Okay, why 37%?
So this is one example of a very precise recommendation that we get from thinking about the mathematics of problems that people face in everyday life, but that have also been carefully analyzed by computer scientists and mathematicians. So in this case, the problem is one that's called the secretary problem, and it comes from a class of problems called optimal stopping problems. So in the secretary problem, you have a pool of applicants for a position, and since this was coined in the 1960s, these are applicants for a secretarial position. And what you have to do is interview each of those applicants in turn, and for each one, decide whether you're going to hire them or have them leave and never come back. The problem is that you don't know how good the applicants are until you've basically started to interview the pool. So you can only evaluate them against one another. And so there's intuitively a mix of looking and leaping that you have to engage in. So you have to spend some time investigating, and then you have to be ready to make an offer. And the math says 37%. That's you spend the first 37% of the pool gathering information. So if you have 100 people interviewing, that's 37 of them. And then after that, you make an offer to the next person who's better than anybody you've seen so far. What you're doing is, out of those first 37, setting a standard that then you're using to make sure that the person who you end up making an offer to is very likely to be the very best person.
So you do not want to be the 39th person interviewed?
Well,
probably.
If you're the best person, then it's good to be the 39th, because after 37, they've set their standard, and you're going to be the next very good person, and so you're probably going to get hired.
Gotcha. Let me also ask the question that I suspect people at home are asking right now, which is, you're from the States, obviously, and you're not, obviously. Where are you from?
I was born in the UK, and then I grew up in the UK and Australia.
There you go. You know what? Because I'm hearing Australian and I'm hearing British, and I couldn't figure out which it was, and the answer is both.
That's right.
You're a lost Bee Gee brother or something like that, aren't you? Just like them. Okay. Let's do the same thing then, Brian. Driving down the street, looking for a parking spot. We've all done this. We've all tried to figure out, the math and the probabilities of, do I go around the block one more time or sit tight?
Right.
What do algorithms tell us about that?
Yeah, this is part of the same class of problems known as optimal stopping problems. So similar to hiring a secretary or looking for an apartment, you face this decision when you come to a spot, which is this spot good enough to take? Should I just commit? Maybe there's something better down the road.
Closer.
But you don't know, and you give up that opportunity if you want to keep looking. And so we include a handy chart in the book that you can cut out and tape to your dashboard. It turns out it all depends on the occupancy rate of how many spots are taken, how many are available. So, for example, with an occupancy rate of 90%, you should wait, I think it's 6 or 7 spots before your destination. But with an occupancy rate of 99%, which is the case in a lot of big cities, you should be willing to commit as many as 69 spaces, which is about a quarter of a mile before your destination.
A quarter of a mile?
So yeah, in fact, thinking about parking as an optimal stopping problem gives us a little bit of advice for urban planners, which is that High occupancy rates, if you think about going from 90 to 99% space is filled, that's not that many more cars being accommodated, but it doubles, or in this case multiplies by tenfold, the distance that you have to walk, and it intensifies the problem of figuring out whether to park or not.
Do you know of anybody nerdy enough to have cut out that handy-dandy chart from your book and actually put it in their car so they can figure out the probabilities when they park?
I think we are perhaps nerdy enough to do such a thing, but to our knowledge, no one's taken that advice to heart yet.
Gotcha. Okay. Let's get a little more, let's raise the stakes here, shall we? Okay, Tom. How about not picking a parking spot, but picking a life partner? Do algorithms help you with that?
Well, the good news is, yes. And in fact, mathematicians have tried using them. So the secretary problem, one way of viewing it is as a description of the situation that you face when you're dating, right? You have a pool of applicants and you're trying to figure out, of those people, who is the one who you should be spending the rest of your life with, and you're going to make an offer to that person.
Well, hang on. I'm going to stop you right there. I'm going to stop you right there because I'm not following your analogy. If you're going to hire a secretary, you may take 100 resumes and then say, okay, one of that 100 is going to be it.
Right.
If you're looking at a life partner, you may want more than 100 options, right? I mean, you're talking about somebody you're going to spend the rest of your life with. Maybe,
yeah.
probably.
Well, so the way that it's been broken down by the mathematicians who've got into this is to say you've got this period between, say, when you're 18 and 40, say, when you're sort of engaged in this search. And so one of the nice things about the 37% rule is that it doesn't necessarily have to apply to just the number of people, but it can also apply to the amount of time that you spend searching, assuming that you're going to have a sort of constant rate of new potential applicants. So the idea that comes out of that is that if you've got from 18 to 40, then around 26.1 years is the moment when dating stops being fun and starts getting serious.
26.1 years. Okay, how old are you?
I am 37.
Oh, you're well past that. How old are you?
31.
And did either of you use algorithms in deciding, first of all, are you with anybody?
I'm engaged, yeah.
You're engaged.
And Tom's married.
Okay, Tom, did you algorithmically put your spouse through the paces before making that decision?
So I can tell you another bit of math. But so Brian actually is the one who used the closest to this algorithm. And so he can tell you the story of that. In my case, my wife and I have been together since our early 20s. So not consistent with the 37% rule, but consistent with another version of the secretary problem. So remember, in the original secretary problem, you don't know how good the secretaries are.
Right.
But you could say in the dating setting, you actually have a sense of how good people are as potential partners. You have a sense of what's called the distribution of those partners. And so knowing the distribution changes the rule that you should follow. If you know the distribution, then that means that you can set a threshold. And what the math says is that as your time searching goes on, your threshold should get lower and lower and lower. But if you see anybody at any point who passes that threshold, then you should propose to them straight away. And so my wife is just fantastic.
Does she feel the same way about you?
Well, she'd have to.
Now, you see, one could infer from your example that you didn't pick the best possible match for yourself, but you picked the best of the lot that you had met so far, cognizant of the fact that there may be something better out there as well.
Well, like I said, if we know what the distribution is, we don't have to worry about that.
Okay.
So that whole period of looking before you leap is about establishing what the standards are. But like I said, Brian has a better algorithmic story.
Well, yeah, I mean, in my case, my fiance was the first person that I started dating after I was 26.1 years old. And as she tells it, I don't recall this conversation, but it sounds like me. I said something to the effect of, well, we're past the threshold, so if this thing really works out, I'm all in. And I was.
And it passed the threshold and you were all in.
I was all in.
And how long are you married now?
We're getting married next year.
Oh, that's right, you're engaged, you're not married yet. Okay, and they said it would never last. Good for you, isn't that terrific? Is there any concern that this takes some of the, what do you want to call it? I mean, I know, we're kibitzing around a little bit here. You didn't get married because you passed the threshold and the algorithm said it was a good time, although there's a little bit of that in there, I'm seeing. Right. But do making decisions based on these criteria take any of the spontaneity, the joy, the romance, the kind of, serendipity out of life? What do you think?
I mean, I think it's ultimately, I mean, we don't prescribe that one live slavishly by these specific rules, but I think they do give us a way to kind of bolster our intuitions. You know, I can remember being a teenager, for example, and being in a relationship when I went to college and asking myself this question of, how do I even know how good this relationship is? This is the first one I've been in. And the same thing goes for apartment hunting and home buying and all of the different scenarios we cover, which is that we do have some gut intuition. And in many cases, the computer science validates that. And we look at plenty of cases where the verdict from computer science, surprisingly, is think less. Just make the decision on gut instinct. Don't consider any more options. Don't gather more information. And so knowing that that is part of the quote-unquote fully rational solution, I think gives us license to follow those instincts and feel a little bit better about it.
Let me do one more example on this, and I don't recall seeing it in the book, so if I'm wrong, you tell me. But most people have found themselves in the kind of a predicament where they want to go to a hockey game or a baseball game or a concert or something like that. They go down to the venue, and they don't have tickets, and they need to buy scalpers tickets. And the question always is, you know, do I let the first guy I run into hit me up for tickets, or do I try and see what else is out there, knowing that I might miss my kind of one opportunity to get something? What do algorithms tell us in terms of helping us figure out that conundrum?
So that's another kind of optimal stopping problem. It's analogous to a situation of doing something like, you know, selling your house, right? So in that case, there's a cost that comes for waiting for offers, right? So in the basic secretary problem, you have these candidates who are coming through, you just get to interview them, and the only cost is that you don't have a secretary. In the house selling problem, you have a series of offers coming in. Your goal is to maximize the value of the offer that you end up getting. And what's happening is that you're paying a price for each of those offers. So you have to wait till you have to make your mortgage payments and so on. So waiting for the next offer costs you a certain amount of money. Or in the case of trying to buy tickets, it costs you the chance to go to the show.
Exactly, because you don't know if that first guy is the only guy.
Yep. So again, there's a nice, simple solution for it, but it's something which, you know, again, you have a threshold. So you should start out having a potentially high threshold, and then as the relative cost changes, you should lower that threshold.
Let's try this. Brian, humans programmed computers to organize files in a very efficient way. If we know that that's what's most efficient, why don't we do that already?
Great question. So we take up this the consideration of order versus mess in two different chapters in the book. And in many cases, the interface that the computer presents to you, that everything is in a folder, everything is perfectly alphabetized or sorted, is a little bit of a lie. What the computer is actually doing to manage its own memory under the surface looks a lot more like a messy office desk with piles stacked helter-skelter. And the principle here is what's called caching. And so the basic idea is...
Spell that.
C-A-C-H-I-N-G, caching. And the basic idea is you want the things that you're going to use most frequently closest to hand. And so it makes sense to have a certain amount of your stuff just kind of piled up on your desk rather than neatly filed away. And specifically, it should be piled in order of the last time you touched it or used it. And so this is one of those funny cases where we all have kind of a stack of documents on our desk somewhere where when we're done handling something, we just slap it down to the top of the pile. And here computer science tells us we don't need to get organized because, in fact, this is the optimum structure for that information. We have perfectly organized it just by this lazy process of putting the last thing we touched on the top.
I tell people that all the time. They think I'm crazy, but I'm with you. I think that makes perfect sense.
Now you've got the proof to back it up.
Thank you. How do computers help us minimize regret?
That's a great question. So I think this also ties into something that Brian was saying in response to your question about emotions before. That I would say that one of the benefits of learning about these algorithms is that it saves us from a certain kind of emotional cost as well, right? So knowing that you're following a good algorithm to begin with is something that can help you reduce anxiety, where you might not know if you're doing the right thing. And often when we're making a decision, we tend to focus on the outcome of those decisions and say it was a good or a bad decision based on what happened, rather than the process by which we made that decision. And knowing that you're following an optimal process is something that can come with guarantees. So in the case of regret, for for the problem of trying to decide, say, what restaurant you're going to go to, or another problem where you've got a fixed set of options, and those options are things that you're going to have a chance to go back to again and again and again, one of the things you have to do is decide, am I going to go to my favorite restaurant, or am I going to try a new restaurant? So this problem is one that computer scientists call the multi-arm bandit problem. Imagine a casino. There are slot machines. You're trying to figure out which slot machine pays off the best. You have to pull the arms on a bunch of those slot machines, like going to a restaurant, trying it, and seeing how good it is. And so in this case, the problem of minimizing regret is trying to minimize the number of times you pull arms other than the very best one, or you go to restaurants that aren't the very best restaurants you could be going to. And computer science can't guarantee that you will have no regrets, but it can guarantee that your regrets will grow relatively slowly. And so you can say that the rate at which those regrets accumulate, if you're following an optimal algorithm, will be decreasing over time.
Do you think following computer logic, being Spock, ultimately makes us happier?
Well, first of all, we'd say that Spock isn't necessarily the best poster child for the kind of things that we advocate in the book. So one of the intuitions that we have about decision making is that being rational means considering all of your options, always choosing the very best one, and producing exactly the right answer every time. And we kind of think about that being the way that computers work. And that's kind of our intuition about what it means to do a good job of solving a problem. But in fact, when we look at computer science and we look at the way that computers solve the challenging problems that are like the ones that we face in everyday life, we see that those problems are so hard that in fact computers have to take different strategies, not necessarily considering all of your options, because you're trading off the cost of gathering more information with the value of actually making a decision, not necessarily being deterministic, like using chance as part of a solution, and using approximations to make problems easier. And so a lot of the things that we think about as being kind of human patterns of reasoning and potentially deviations from rational behavior, in fact, fall out of thinking about rationality more from the perspective of trying to minimize computational cost at the same time as trying to maximize the quality of those decisions.
So let's finish up on this then. Brian, if we take your advice and all of the major decisions we make in our lives are done algorithmically speaking, are normal other people going to think we're jerks?
On the contrary, we advocate explicitly for what we call computational kindness. And this is an idea that the way that we interact with each other implicitly and explicitly poses them computational problems to solve. If we're deciding where to go out for dinner and I just say, oh, I'm easy, conventional etiquette would say it's polite to defer to you. But computationally, I'm also saying, well, there's this problem that we have to solve jointly, and you solve it. And so the principle of computational kindness runs counter to some of what we normally think of as good behavior. But it's a way of bridging the gap between computer science and ethics, and a way of thinking differently about how we interact with one another.
Well, I have to tell you, when we considered putting this segment together, we did consider 37 other sets of authors on computer books. But given that optimal stopping was at 37, we just thought, okay, yeah, you guys will do it. Okay. Tom and Brian, it's great to have you at TVO tonight. Thanks so much. Algorithms to Live By, the computer science of human decisions. Thanks so much.
It's a pleasure.
Help TVO create a better world through the power of learning. Visit supporttvo.org and make a tax-deductible donation today.